Hi everyone, now we are performing an experiment, that is Hall effect. At first of all, what do you mean by Hall effect? The Hall effect is nothing but when a magnetic field is applied perpendicular to a current carrying conductor, a voltage is developed across a specimen in a perpendicular to both the current and the magnetic field. This phenomenon is called Hall effect, and here this is known as the Hall probe, where here this is our specimen, and this is we are using here germanium. Here it is written Hall probe and germanium crystal, and these two are connected to the voltage, and these two are connected to the current source. We can observe it. These two are connected to the voltage. The red wire is connected to the voltage terminal, and this green wire is connected to the current terminal. So next, this is stand for Hall probe, and this is an electromagnet of specific distance. We have to measure this distance later. And this is digital Gauss meter. At first we have to turn on the all the setups, 1 2, and then Hall effect. So at first, this is no need of this one at the starting of the experiment, so we need to switch off it. And then here I am connected for the low concentration, and this is known as Hall probe. This is Hall probe. What we need to do is just by then we have to place it in between this one, and then the digital Gauss meter must show 0, so that we have to keep it by using the stand. Now we have fix it for the stand, and then what we need to do is we have to calibrate it for the Earth's magnetic field, that is by away from the electromagnet, and digital Gauss meter must show 0. Okay, now it's 0, and then take back and mount it in between the electromagnets, and this is the aim of the experiment, to determine the Hall coefficient RH of a given semiconductor, that is given is germanium crystal, and a carrier concentration of a specimen, Hall mobile of charge carriers, and relaxation time. The formulas are RH is equal to VH divided by I, where I is the current, VH is the Hall voltage, and T by B, where B is the applied magnetic field, and T is the thickness of the specimen, where it's given as thickness is given, and it is already written here only. The thickness is of 7 mm. Then we need to plot a graph of the slope, that is VH versus I, in the graphical representation, and T by B remains constant, and the formula for Hall coefficient is equal to 2VH divided by IH, that is Hall voltage divided by Hall current. At first we have to take for the readings, that is current in amps. We have to increase current, the constant current I 0.5, 1, 1.5, 2, 2.53, and magnetic field in Gauss we have to note on from the digital Gauss meter. Next, first we have to increase it for 0.5, 4, and one thing we have to keep in remember, that we should not increase and decrease, we should not do that. We have to increase it in a certain way only. That is, now the digital Gauss meter shows 520, 582, that is for 0.5, 582. In Gauss it is 582, same. And then we have to increase by 1. The experiment should be performed very slowly, because all the experiments and all the setups are very delicate and very sensitive. Now for 1 it is 985, 986, and then again for 1.5, 1.5 it is 1426. Later on it shows it will be for some digital current it shows it stops. So that what we need to do is by multiplying it into the 10, that is approximately in the region of after 2.1 amps, after 2.1 amps it will be at the 0. Then what we need to do, we have to shift the reading by pressing this one, and it will be 203 into 10, that will be in for 2.1. Here 2.1 it will be 201 into 10, that is equal to 2010, that is equal to 2010. In magnetic field in Tesla is 2010 into 10 to the power of minus 5. Already it is written here. And then later what we need to do is, by now turn off the digital gas meter, and take the Hall probe away from the setup and close it very neatly, because it is very delicate and it is very sensitive also. So that, and then reduce it for the minimum current. Now turn on the Hall effect board